Anybody wants to say like that, what the highlights were? Was it more of an expository talk? Or?
Interactive.
Oh, yeah. More than usual? More than usual example? Okay. Yeah, I think that comes with as you grow older, I think classes become more interactive. Alright, so yeah, so I'm glad you guys enjoyed it, and hope it was a good break for you also. Okay, so alright, so we'll continue where we left off last time. I was hoping to finish this small thing. So today's lecture will probably be a little shorter than usual because I was hoping to do something about online algorithms. I don't think I will get there. So I thought might as well finish optimization and say a little bit more about this. Okay, so that's the plan for today. And as all of you know, homework 5 is due next Wednesday. And someone asked for lecture notes, and because I was traveling, I couldn't put it up. But I will put, I think for one of the lectures, it's useful to put it up, which is for the balls and bins. I will do so either tonight or tomorrow morning. So, yeah, so that's just something. And, good. So we were looking at, most of last week at optimization, and we said that generically optimization looks like this, but we are interested in using optimization for combinatorial problems, the kind of problems we've been seeing so far. And we said that this is the general framework that we wish to use. So you have this instance of your combinatorial problem, so you have some graph or something, and what you do is you try to phrase the problem you want to solve. Let's say it's a minimum spanning tree or matching or something like that. You try to phrase it as an optimization problem. Right? So you come up with some variables and some constraints, some objective and so on. And then you feed that optimization formulation to a solver. Okay, and this we've been assuming is a black box that just takes this program and comes up with the optimal solution. We haven't been caring too much about how it does this. And optimal solution can look like this. In general, if it's a continuous optimization problem, it can look like some 0.5, 0.4, something like that. And the key point is that from here we need to get to a solution to the original problem. And the important thing is that, of course, this is what I keep saying, is that you have to prove that this optimization formulation captures everything you want about the problem statement. And you must be able to go from a solution of this optimization formulation to an instance. Alright? And yeah, and like I was saying, there are three important things that you should ensure. So first is what are the variables, and then what are the constraints, and what's the objective. Okay, so that's the usual thing that we study about when you're looking at a formulation. Okay, and we looked at a whole bunch of examples, some of which were easy. We said that we saw that this turned out to be pretty easy. This was also fairly easy. This one required exponentially many constraints. And we also had some interesting discussions last week about what kind of constraints are allowed. And we said that basically anything, but we would prefer simple ones, because optimizer performance depends on how these constraints look like. Okay, so if you have some weird polynomial constraints, most optimizers will not be able to solve this optimization problem very well. Okay, in which case the whole setup is worthless. Right? Okay, so this is where we were, okay. And we also started asking, so when does when can an optimizer work efficiently? And we said that there are very few answers where we provably can say that it can work efficiently. And these are something that you should remember. So the only thing that, only things for which we know, we have some guarantees that, that the optimizer works efficiently are things like linear programs or convex programs. Okay. And basically anything that you, I mean, there are a few other exceptions, but these are like the big classes that we know to do well. And like I was saying last time, so for problems like integer linear programs, which if you think about it is what we've been doing when it comes to like set cover, matching and so on. So these can also be solved fairly well. There are also some heuristics for like quadratic programming and so on. Okay. So this is something about when you can actually solve these problems. Okay, so right? And we started out with this general goal of, okay, so let's now see how you solve combinatorial problems using this framework, right? So, okay, all right, so I don't have this. Okay, so, the general goal is goal or question is can we solve combinatorial problems? Example, set cover using optimizer. And we want to do it not just using a heuristic as a heuristic, but you want to actually do it with some guarantees. Okay. And this will be the general goal of today's lecture. So we'll look at vertex cover and set cover, and we'll show that this way of optimization formulations actually can give you some interesting guarantees. All right. So, okay. So going back, right. So what we know is that you can solve linear programs efficiently. And as I said, linear programs are ones in which you have real valued variables, linear constraints, and a linear objective. So these are like continuous optimization problems. So let me even write linear. Linear programs. These are continuous optimization. And the question we asked last time is, choose going from discrete domain to continuous. So this is the question which we roughly speaking stopped at last time. So let me just anyway do this. So for vertex cover, if you remember the problem, here we are given a graph. And the goal is to pick a small set of vertices such that every edge so this is what we did in a couple of homeworks ago. So we said that you want to monitor some roads, and you can monitor a road if you have a camera at one of the endpoints. And abstractly, this is the problem. And you can write it as an optimization relaxation. So yeah, actually, what are the variables? What variables should you choose? Remember, variables should be linked to the solution.
Whether a vertex is chosen.
Yeah, so you have a variable for every vertex u, and you say that xu is supposed to be 0 or 1, and indicates if it's chosen. And we want every edge to be covered. So for every edge u3, you say that xu plus x3 is bigger than or equal to 1. And your goal is to pick the smallest set of vertices, right? So your objective is to minimize sum over all u of it. And these are the only constraints, right? So any 0-1 solution that satisfies this and this will actually be a valid solution to the problem, right? Because you will cover all the edges, and of those you want one that minimizes the sum of x. Okay, so this is more of a recap of what we did. Okay, and why is this not a linear program as such? Yeah, so you have these discrete domains, so it's not a continuous optimization problem, right? So remember, in linear programming, you just have continuous variables, and you have some linear constraints, and you have real valued variables basically, right? So you don't. So this constraint is not. And we said that there's an easy fix for this, and the fix is moving to what we call a relaxation. Okay, so this is a notion that you should be very comfortable with. If there is something in optimization that you should really know, it is this kind of a notion, which is relaxation. And the relaxation basically changes integer or discrete variables into continuous ones. And in this case, the most natural way is to just say that I want xu to lie between 0 and 1. And this is like, these are two constraints, and they just say xu should be bigger than or equal to 0, xu should be less than or equal to 1. And each one is just a linear constraint. And then you also have for all edges xu plus xu bigger than or equal to 1. And objectives. And for most problems for which you can write some 0-1 formulation, you can write some kind of a relaxation. Okay, and this is called a linear programming relaxation or an LP relaxation. Okay. So this is a very, very basic idea in approximation algorithms. So it will keep popping up, keeps popping up all the time if you try to read some kind of approximation algorithm paper. Okay. So LP relaxations are one of the main tools in approximation. All right. So far so good. So you had an optimization formulation, you converted it into a linear program, and now suppose you had a problem and you wrote this thing and you solved it, right? So what is, and you came up with some optimum solution, right? So what is the candidate problem that you have? What is the candidate problem? I mean, can you now go back? Remember, in this framework, you started out with a problem, we wrote an optimization formulation for it, you fed it into the optimizer. And what I'm saying is, instead of feeding this optimization problem, let's say you fed in this optimization. Now what I said before ensures that the optimizer can solve this really quickly, okay, because we know that linear programs can be solved very quickly. And then it produces some solution. But so what could be an issue with the solution that it produces?
Predictive is not a binary value.
Yeah, so if you solve the relaxation, you get some feasible solution to this, to all of these constraints, and you will try to minimize the sum of ux. Right? So what you can get is what I would call cheating solutions, where optimum solution the LP. Okay, LP always means linear program. So need not have Let me show a very simple example of vertex cover, where the optimum solution to this integer program and the optimum solution to this LP relaxation are different. Okay? So for example, so let's consider this instance of vertex cover. Okay, so it's the most like the simplest you think of. So it's you have a triangle and you have 3 vertices. What is the size of the minimum vertex cover for this example? 2, right? It's like you have to pick at least 2 of these edges. 2 of these vertices. Like you can pick any 2, that's fine. In order to be able to cover all the edges, because otherwise, if you only picked 1, let's say you picked 1, then this edge is uncovered. Similarly, if you pick this guy, that edge is uncovered. Okay. So size of the optimum vertex cover equals. Now, what about the optimum value of this LP relaxation?
1.5.
Okay, so why is it 1.5?
Every variable assigned a 0.5.
Right. So if you give x, if you set your LP relaxation, opt value of LP relaxation is actually smaller than equal to 1.5. In this case, it is not smaller, but it's equal to 1.5. But in general, you have produced one solution, so that only tells you that the optimum value is only smaller than that, right? So this is less than equal to 1.5 because xq equals xp equals satisfies all the things. Right, because x1 plus x2 is bigger than equal to 1, x2 plus x3 is bigger than equal to 1. And all of them lie between 0 and 1. Okay. So any questions about this? So it's a very simple example, but it's important that you understand what is actually going on. So the example itself is not. Okay, so what this shows is that in general, the value of the optimum solution, so this is the value of this value of original formulation. And this is the value of the relaxation, and these can be different from one another. And this sort of a thing is called it's called the integrality gap. Okay, so the ratio between the optimum, the true optimum value and the optimum value of the self-healing relaxation is often called the integrality gap. Okay, and as the name suggests, it's like, I mean, in some sense, it is the gap between an integral solution and a fractional solution. Right? So, integrality of this. So this is just a common notation. So, yeah, it's not good. All right, so that's definition. Okay, so what this tells you is,
Yeah, I was just curious, why is it an upward bound as opposed to an Is that just because of the way we're framing optimization?
oh yeah, so right, so why you're asking why I wrote less than or equal to and not equal to, right? So in this case, it happens to also be 1.5. But remember, you have this optimization problem, and I gave you one solution to it, right, which is all 0.5. Okay. There could, in principle, be a better solution. So that's the reason I wrote that it is less than or equal to 1.5.
Because we didn't necessarily minimize it.
Yeah, you did not necessarily minimize it. You just came up with one solution where the value was 1.5. Yeah, so this is an important point. So, yeah. Okay, so is it clear what he was just asking? Saying why did I write less than equal to 1.5? Because I did not prove to you that there is no better solution than all half. Okay, so far so good. And so the next question that we would like to ask is, let me ask two different questions. Okay, so the first question is the integrality gap potentially very large? Okay, like, can it be? Yeah. Right. So in this case, the gap was the ratio of this 2 divided by 1.5, which in this case is like 4/3. Okay, so it's more than 1. But I'm asking you, can it be really big? Okay, like, can it be 10? So that's one question that we'd like to answer. Okay. And a second question is, which is very closely related, is there a simple way, or I mean, need not be simple, but is there a way to go from a fractional solution x to an integral one without changing the objective value? So is this question clear? So I'm asking you, so this is the process called rounding, okay, and it is what you would think. So you have this fractional solution, x1 through xn. You want to go from there to an integral one without the objective value being changed too much. Okay, so it can change a little bit, but you don't want it to change too much. Okay. And note that this question is related to the first one. Do you guys see why?
Because if the gap is small, Then you can round you.
So it's the other way around, right? So if you can actually round, let's say I have a fractional solution, and I can go to an integer 1 without changing the objective value too much, then it means that the gap is not too large. So the gap is basically bounded. Yeah. So, right, because I mean what you said is also right, but it's just that maybe the integer solution had nothing to do with the fractional one. Right? So, yeah. Okay. So what I wanted to say is that if the answer to this one is yes, then the answer to this is then the integrality gap cannot be too large. Okay, so then the answer to that is no. So yeah, but anyway, I don't want you to get confused with this. So let's just see the example. Okay, so I think it makes the thing very clear. All right. So the claim is for vertex coverage, we can convert any fractional solution integer to a feasible integer. Note that, I mean, you can always convert it into some integer values, right? But you are interested in actually a feasible integer solution. Let's give it some name. So let's call it some yu, such that sum over yu is not much more. In this case, it's at most 2 times sum over u. Okay. So this is what I'd like to claim. So you can take any feasible fractional solution. You can convert it into a feasible integer solution so that the sum of the u's over this yu is at most 2 times sum over ux. Note that this is the quantity I care about because this is the objective value. So this was the quantity being minimized, right? Okay. And first thing I would like you to notice is the easy corollary that suppose solving the LP a fractional solution whose cost is equal to some alpha. Okay. Alpha need not be an integer or anything. Then we can come up with an integer solution with cost less. So this is what this theorem is basically saying, because sum over xu is the cost, and if you came up with solution that this value is equal to alpha, then that claim will tell you that you can actually come up with an integer solution where the cost is at most 2 times. So assuming that the claim can be shown, do you guys all agree with the corollary? It's just basically a reflection, but yeah. No. By cost, I mean the objective value. Okay. So, right, what you're asking is what if this wasn't the minimum? Right, doesn't matter because it will only be bigger than that. And yeah, all you're claiming is that if you give me a fractional solution where the objective value is alpha, I will give you an integer solution where the objective value is at most 2 times alpha. And it is in your interest to consider the least alpha. Yeah. Okay, so this is a very simple thing. All right. So let's prove this. Okay, so this actually turns out to be surprisingly easy. So what is a natural rounding procedure that you can think of that allows you to go from fractional values between 0, 1 to integer values, binary values 0 or 1?
It is less than 0.4 or 0.
Yeah, so you can always say, okay, just if it's strictly less than half, this is, as a coincidence, this is one of the few problems where this actually works. Okay, so the natural rounding is if xu is less than equal to 0.5, sorry, is strictly smaller. Actually, this is a subtle thing which is important. That's strictly less than 0.5, then set yu equals 0. And if xu is more than equal to 0.5, set yu equals 1. And what is the claim saying? Right? So the claim is saying that if xu was a feasible fractional solution, then yu is actually a feasible integer solution. Which means that you have to say that if you produce a yu like this, it remains feasible. Okay. And what does it mean to be feasible? Right? Like we just have these constraints. You've got to show that if xu satisfies all of these constraints, then so does yu. Okay. So, yeah, can you guys think of why this should be true? Yeah?
So for an edge, you know that the sum of the two vertex weights is at least 1, so one of them has to be at least a half. And so that one will be rounded up and will remain in the solution, the edge stays covered.
Okay, so that's excellent. So what she said is, you know, yeah, it's these constraints are something you don't have to worry about. You're still replacing xu with 0, 1. So all you have to check is these constraints. And if your x satisfied the constraint, so let's say xu plus xv was at least 1, then it could not have been that both are strictly less than half, because then their sum won't be more than 1. So at least one of them should have been at least a half. And then our rounding procedure would have then rounded up that one to 1. So the proof is actually this one line. So if xu plus xv was at least 1, then one of them implies yu is equal to 1. And that's it, right? So which means that yu plus yu. Okay, so y also satisfies the constraints. Okay, so this is nice. So it shows that the rounding that you do like that always remains feasible. So now for the second part, there were two parts to this. First we said that this is a feasible solution, and then we wanted to compare the cost. Yeah.
Is the vertex cover supposed to be connected, or can it be disjoint groups?
Yeah, it can be disjoint. Yeah, it's just some set of vertices that covers. So yeah, so now how do you compare this cost? This is also equally easy. So you can see. Yeah.
Is 0.5 we convert it to 1, right? Now suppose that we have n of those. So both of them multiplied to n. Still the ratio is 2. So that gives us that 2.
Yeah, so his intuition is correct. So what he's saying is, if your objective value, so what he's saying is that if xu happen to be a half, then you're making it 1. If it's less than half, you're making it 0. So y is only smaller than x. Okay, and if it's more than a half, then you're going from some, let's say, 0.6 to 1, and the ratio of those two is only smaller. So that's his intuition. And yeah, so in fact, there is a much easier way of saying this intuition, which is just observing that for any u, okay, the rounding satisfies yu is less than equal to 2x. Okay, because if xu was between half and 1, this is trivially true. If xu was less than half, this is you would round to 0, so this is again trivially true. Okay, so this is a simple observation, but you have this for any single u. And if you have this for each u, then you can conclude that the sum over u of yu is less than equal to 2 times sum over u. Okay. Yeah, I mean, we could also say what you're saying, but this is, I think, a little bit of a sleek proof. Yeah. Is there any comments, questions? Alright, so this is good. So what this shows is that if you have any fraction solution, you can convert it into an integer solution with at most twice the cost. And this is nice because now you have, so let me get this slide. Okay, so now what we have obtained is now what we call a factor 2 approximation. Because recall what we did, right? So what did we do? We started with, so this is some instance of vertex cover. Okay. We started by writing this optimization formulation. And this had x u belongs to 0, 1, and it had a bunch of constraints. And this we converted into its LP relaxation. And the goal was to minimize some over u. LP relaxation had the same things, but it had the same. So this is the same except that changed to that. And this one, we feed it into this optimizer, and I told you that optimizers can solve LPs very fast, right? Like linear programming, one of the things you can do very well. And this gives us some possibly fractional solution. Okay, so it gives some values in 0, 1 for different xq. And now what I'm saying is that this process of rounding, okay, and now I do this. In this case, the rounding is just trivial. It was just increasing the cost. And I have just argued that the output of rounding is actually a feasible solution to the original problem. Okay, so we have added this one extra step of rounding to our original previous framework. Okay, so this is what, and this is this framework called rounding and LP relaxation. And basically, all you do is you start with the optimization formulation, you go to a relaxation of that. This relaxation you can solve very quickly. But you get some solutions that are not feasible for the original stuff, for the original problem. And then you perform this rounding, which will give you something which is actually feasible. And then that gives you a solution. Okay. So is the mechanics of this clear? Okay, so this is how at least you solve it. Okay, so now what we have done, we've also analyzed the costs, right? So let's say the optimum value for this problem was let's call it some alpha star. Okay, so alpha star is the optimum objective value for that problem. What is the optimum objective value here? Yeah, it's the same because it's capturing the problem exactly. Okay, so it's also alpha star. What is the optimum objective value out here? What is the optimum objective value over here? Why is it half? So far I'm not doing anything, right? I'm not doing any rounding. Right? So I'm asking you, what is the optimum to this, to the LP relaxation? Yeah?
Something that's done.
Yeah, it is something that is at most alpha star, right? Because you started with this formulation. The only thing you have changed is you've changed this xu belong to 0, 1 to xu between 0 and 1. Okay. So you've added a few more potentially feasible solutions. So, and it's a minimization problem. So the value only drops. Okay. It may strictly drop, it may not. So what you know is that this is at most alpha. If you remember in this triangle example, this alpha star was 2 and this was 1.5. So there it strictly dropped in the triangle example. In general, it may or may not drop. So, but this is what that is. Alright, so that's good. So this one is less than equal to alpha star. So the optimizer will find it and it will find the best values. So since the optimizer is actually finding the best alpha star, it will return something whose value is actually whatever that is. So let me call this beta star, which this is the actual value and this is less than or equal to alpha star. That's what I agree. That's like the 1.5. Yeah, beta star is 1.5. And this guy has value that is equal to beta star. Right? Because the optimizer was actually solving this one exactly. And now what I told you by this argument in the previous slide is that we have a way of taking a solution with a certain cost and converting it to an integer solution of twice the cost. So if you had a value of beta star, it was producing a solution to the original thing of value 2 times beta. Yeah, in this example, 2 times beta star would be like, for instance, 3. But in general, this is always smaller than or equal to 2 times alpha star. Okay. So, and this is exactly what we mean by a factor 2 approximation algorithm, right? So, a factor 2 approximation algorithm just means that if, suppose the optimum value is some alpha star, you produced a solution that is smaller than or equal to 2 alpha star, right? And this is exactly what we have done in this process. Okay. So this whole thing is called the relax and round paradigm. For designing approximation. Okay. And it's a very simple framework, but it turns out to be very powerful for lots of problems. Okay, and often each of these steps will be pretty involved. In our case, going from often going from here to here is trivial. It's the same thing. Okay, but this rounding process is often the tricky step. So, any questions on this full framework? Because this is something that's, I think, very nice, and there's something about optimization that you should like really remember. It should be good. Yeah.
Also to use 2 intervals instead of 0, 1 for variables. For example, 0 to epsilon and 1 minus epsilon to 1 to get 1 plus epsilon approximation.
Yeah, so what he's asking is that here we did the rounding in a very kind of a naive way. Right? Like you can imagine, maybe you picked lots of intervals and maybe you did something a bit more smart. But the point is that ultimately you only have these 2 values, right? And if you have a solution that's a bunch of halves, you still have to do something to make them 0 or 1. You can't let them be half, right? Yeah.
But if you have variables between 0 and, for example, 0.1 and 0.9 and 1.
Right. So if it so happens that most of your values are pretty close to integers, like if you have values that are somewhere between, let's say, only in this interval and only in this interval, let's say nothing was very close to a half, then you can get much better guidance. In fact, this is one of the examples from practice exams, if you've seen, okay, from a couple of years ago. Okay, so it's just this based on observing what he just observed, that this whole thing is tight only if you had values that were very close to half. If you were somehow promised that values were always kind of quite big or quite small, then you can get a much better approximation ratio. Yeah.
I did not go for near to integer values. We use an LP 2 intervals instead of just 1 interval to minimize the solution.
Yeah, but how do you say it's either this or that, right? That's very hard to write in a linear program. Right? So, yeah, that would be nice if you could say that in the program, if you could say XU either lies between 0 and half or 0 and 0.1 or something. one could do that, one would be more aggressive and just say can lie between 0 and 0 or 1 and 1. So, yeah.
So we could add a condition like for any edge, uv xu cannot equal u xv, right? That would have an equivalent thing of
Right. So that's again a problem, right? So how do you say that it's not equal in a linear program? Right. So at least I don't know of a clean way of saying xu not equal to xv by just using linear constraints. You could say,
If you is less than if C and if C is
right, but strict equality is not allowed in yeah. Yeah.
for the proof, the key was the how you round the
Yes,
number.
yes.
So if it was less than or equal to 0.5, then we are not able to get this one, right?
If it was yes, yeah.
So if it was, then what would be the range? Still they have
So
a
if
range.
it was, so his question is, this is something that I was saying when I was doing this. So suppose I accidentally write this rounding as less than or equal to 0.5 and this one was more than 0.5. Then what goes wrong? Does this step fail or does this step fail? The first one fails, right? So now you no longer have a feasible solution. Like the all halves was feasible for the fractional program, but you are rounding all halves to all zeros. So that is so that's the reason. So feasibility fails in this case.
So we cannot have a limited gap, right? We can do vertical.
Yeah, in this case though, I mean the gap cannot be more than 2, right? That's what we showed.
Yes.
Yeah.
But I mean, if it was equal, then the gap would be large, right?
No, then it's just not feasible. So there is not even a question of gap.
Okay.
Yeah. So you have to produce a feasible solution. Yeah, because I can always say I produce a zero solution, it's not feasible, but it has a really tiny cost. Right? So that's not enough. All right. So that's great. So I think so. This is a simple picture that you've got to remember. Okay. So this is maybe it's nice to draw boxes. Because these are optimization formulations. And this is what this gives. So let's now look at, I wanted to do the set cover problem. I don't know if I will be able to do it in too much detail, but let me do in a slightly hand-wavy manner. Okay. So what are so this problem is very similar to vertex cover. So I thought, but here the rounding is not as simple. So that's what I'd like to illustrate. Okay, so the problem is the following. If you have, again, just to recap, so we have N people and M skills. And our goal is to pick as few people as possible so that they cover all the skills. This was the set cover problem. And we said you can write the same kind of an LP. You have variables xu for people, if they are chosen or not in the set. And we say that variables xu constraints for each skill sum over u and forget what we called this set. Do you call it S sub j or S of j? Wait, yeah. Okay, so this is S of j is the set of all people who has the skill j. Oh, S sub j. Yeah, this one I remember vaguely, but forgot to check. Okay, so this is beginning one. Sj is so we have m constraints, one for each skill. And of course, we want to minimize sum over u. So this is a really similar linear program, right? So instead of saying that for an edge xu plus xb is bigger than or equal to 1, now you are saying that for each skill on the right, I look at everybody on the left who has that skill, and I say that that has to be bigger than or equal to 1. Okay, so the sum of those numbers must be bigger than. So the LP is the optimization formulation is exactly the same. Okay, so we have xu belongs to 0, 1 for g for all j. So this is very clean. And now the LP formulation is also similar. So what do you do in LP formulation? Same thing, right? So you don't want discrete variables, so you just say that 0 less equal to xu less equal to 1, and you have the same. And you want to minimize. Okay. So this is what. So this is same. Now the question is, will the same rounding work? Yeah, remember in rounding you want to go from a solution to the LP, the second one, which is potentially fractional, and you'd like to come up with a solution whose values are all 0. So it's the same rounding work. That is, you set yu equals 1 Is this yu feasible? Yeah?
I mean, it can't be, because if you have some, let's say you have 3 people who are, have like 3 nodes who have a value of 0.4 or something like that, their sum would be greater than 1, but if you round down, then we're not going to.
Yeah, so what he's saying is that, here earlier there were just 2 of these guys that were involved in each constraint, right? So the argument was if for like one of them had to be at least a half, so that was getting rounded up to 1. But now this summation has a lot of constraints. I mean, it has a lot of terms, right? So it has, let's say a skill is possessed by like 5 people. So then you have xu1 plus xu2 plus so on, xu5. That has to be bigger than or equal to 1. And if that is bigger than or equal to 1, then potentially all of them are something like 1/5. And then none of them would get rounded up to 1. So this does not work. Because and the example is just, let's say x1 plus x2 x3 is bigger than equal to 1 can happen, but none of the y. If you round like this, if you have x1 plus x2 plus x3 more than x1, then none of these y1, y2, y3 are equal. Okay, so this will not. Okay, so what do you do in this case? Right, so that's so this is where I wanted to. So it turns out that it's not very trivial to round this linear program. But there's this very cool procedure that I wanted to introduce, okay, which is this process called randomized rounding. Okay, so this is it'll tie in with what we've seen in randomized algorithms a couple of weeks ago. Okay, so what is how many of you have seen this thing before? Randomized rounding. Okay, so if not, you should, yeah, okay. So hopefully you will like it. Okay, so it's a very simple procedure, and what it relies on is this very simple intuitive idea. Okay, so suppose we round every x u to 1. So suppose you have a variable. It gets easier with numbers. Okay, so suppose I have an xu which is 0.1 and xv which is like 0.6 and some xw that is 0.8. So what randomized rounding tries to do is I will set yw to be 1 with probability 0.8. Okay, I will set yv to be 1 with probability 0.6, otherwise I will set it to be 0, and so on. Okay, so it's like instead of deterministically saying that, oh, if you're above a half, I will round you to 1, you just say, oh, okay, depending on your value, if you're pretty close to 1, I will round you up to 1 with higher probability. Otherwise, I will round you up with smaller probability. Okay. So it's a very intuitively a very clean procedure, right? Like it's just, yeah, you're trying to, this is what you would try to do if you have to do something randomized. Right? So this is what we do. Okay, so suppose we round every xu to 1 with probability equal to xu. Okay. So now, suppose you have I want to claim that what this does is something that's not so bad. Okay, so what I would like to claim is that to look at is, suppose I have some x1 plus x2 plus x3, which it turns out to be bigger than equal to 1. So let's say this is one of my constraints. Now, as before, let's say all of them were roughly were equal to 1/3. So in the previous rounding, where you only rounded up things that were more than half, none of these guys would have got rounded up. But now each one has like a 1/3 probability of getting rounded up to 1. Okay. So in expectation, you expect one of the three to be rounded up to 1. Okay. So, and that's a nice fact, a nice thing that you can hope to use. Right? So, in expectation, one of the two. Okay. So if you look at your y1 plus y2 plus y3, at least that condition is satisfied in expectation in some informal sense. Okay. So that's the general idea behind randomized rounding. Okay, so to make it actually work, you have to do some more work, which I will show you. But is the idea clear? And note that there is nothing sacred about 1/3 here, right? So like you could have done it with like suppose I had like 100 variables, all of them were 1 by 100, and there were 100 of them. Now you have the same thing. Each one gets rounded up to 1 with a much smaller probability now, but there are 100 of them. So in expectation, one of them will get rounded up. Okay. So that's the idea in randomized round. Okay, so let's see how to make this form. So to make this formula, I want to do one slightly, something slightly different. I would like to say, let alpha be some parameter that I'll pick later. I want to give some slack. Yeah, I don't want. Remember, in the set cover problem, you really want every constraint to be satisfied. You can't just say, hey, this constraint is satisfied in expectation. Yeah, so that's not a valid solution, right? So what we argued here is that somehow each of these, like this constraint, in expectation, one of these guys will be rounded up to 1. But that we may not be happy with in set cover, right? Because in set cover, you really want each, for each of these tasks, you want somebody who's an expert. Each of these skills, you want somebody who's an expert. Okay? So satisfying a constraint is not negotiable. It's not something that can happen in expectation. It really has to happen with hypothesis. So you can think that, oh, okay, so instead of rounding it up with probability 1/3, maybe I round it up with probability some alpha times 1/3, and I will pick some alpha so that things work out well. Okay. So that's what alpha is doing. Okay. So let alpha be a parameter. We will pick it later. TPP. Okay. And suppose we set yu to be equal to 1 with probability alpha xu and 0 alpha. And this does not, strictly speaking, make sense. If alpha is big, you have to say that you have to threshold the probability at 1. So you have to, let's say I say min of 1 comma alpha. Because the probability of 1.5 does not make much sense. So I will always threshold it at 1. Okay. So what we are doing is you set yu to be, so now yu is a random variable. So it's 1 with that probability and 0 otherwise. So now we can bring out all our randomized analysis skills, right? So now we can say, given some, suppose you had this constraint, right? So suppose x1 plus x2 up to some xp was more than or equal to 1. So then what is the probability that y is actually 0? So these are some binary numbers, right? So these are 0, 1 and variables. So if the sum is 0, I'm just asking you what is the probability that all of them get set to 0? So any thoughts?
Minus alpha is equal to power of n.
Yeah, so that would be true if all the xu's were equal, right? So to the power of t, you mean, right? So that would, so what he's saying is, yeah, so it would be like product of the probabilities of each of these guys being equal to 0, because the only way sum of the yi's is yi's is 0 is if each of them is 0, because even if one of them is 1, it will be 1. Okay. So probability of this is 0. So this is equal to one minus alpha x cubed, sorry, 1 minus alpha x1, alpha x2. Okay. So, in fact, I should be a little bit more careful, because for the same reason that I had to be careful and write min of 1 comma that. So can someone say what that would correspond to? Like, if it so happened that one of these alpha xu's was more than 1, then what happens?
One of them should be 0, so probability.
Right, so so in that case, yu will always be set to 1. Okay? So there is no way that sum of yi is actually equal to 0. Okay? So then the probability is actually equal to 0. Okay? So that becomes a trivial case, and so we will not bother about it. Okay? So you don't need to worry about alpha xu becoming more than 1. So you could have picked alpha pretty large and still nothing bad would happen. Alright, so that's fine. So you can always say that this is the interesting case where you have something like this. Okay, so this is fine. So you know by now you should have gotten the hint. If you see 1 minus something, you should always upper bound it by e to the minus that quantity. And so this is something that we've seen multiple homework. So you say that this is at most e to the minus alpha x1 times e to the minus alpha x2 and so on, e to the minus alpha xt. Okay, and this follows because 1 minus a is always less than or equal to e to the minus. This is an inequality that we will always keep using. It's true for all a positive, negative, anything. Okay, so this is what you've got. And now this is nice, you have product of exponentials, so this just becomes e to the minus alpha times sum over I going from 1 through t of xi. Okay. So now you're in good shape, right? So now you suddenly realize that, hey, I can use, this is what I know about sum over ixi. Okay. And this is exactly the term that shows up here. Okay, so this is so from this, so this implies, so this term is less than or equal to e to the minus alpha. Okay, so alpha was some parameter that I said would be TBD. Okay, and what I have proved is that if you start with the feasible x, which satisfies this kind of quantity, then the probability that the y's that you came up with did not satisfy this constraint, okay, which is sum over yt turns out to be equal to 0, probability of that happening is something like e to the minus alpha. So this is what we have shown. Okay, so we are unfortunately out of time, but it turns out that this is one constraint, right? So for one constraint, it's telling you that the probability that randomized rounding does not satisfy this constraint is like e to the minus alpha. And you can pick alpha to be roughly log m, okay, it turns out, and that probability would become something like 1 over m. So you have m constraints and you have like 1 by m probability of one guy failing, so you can argue that none of them will fail with a pretty decent probability. And that's the whole argument. And again, so since we're out of time, I'll leave this as an exercise. You can verify that this results in like a log m approximation. Okay, so this is if you remember, we got the same log m approximation by some greedy algorithm also. And this is like a second way to get a log m approximation. Alright, so let's stop.